The free electrons near the junction in the N region begin to diffuse across the junction into the P region where they combine with holes near the junctions. When the P-N junctions form, the N region loses free electron as they diffuse across the junction, creates layers of positive charge near the junction. As the electrons move across the junction, the P region loses holes as the electrons and holes combine, creates a layers of negative charge, form the depletion region. In the depletion region, there are many positive charges and many negative charges on the opposite side of the P-N junction. The forces between the opposite charges form an electric field. The electric field is the barrier to the free electron in the N region. The potential difference of the electric fields across the depletion region is the amount of voltage required to move electron through the electric fields. This potential difference is called the barrier potential. The typical barrier potential is approximately 0.7 volt for silicon and 0.3 for germanium at 25 degrees Celsius. Voltage source or bias connection are positive to the P region and negative to N regions. Bias voltage must be greater than the barrier potentials, where 0.3 volt for germanium and 0.7 volt for silicon. The negative side of the bias voltage pushes the free electron in the N region towards P-N junctions. Flow of free electrons is called electron currents. Also provide a continuous flow of electron through the external connection into N regions. Bias voltage imparts energy to the free electron to move to P regions. Electron in P region lost energy combined with holes in valence bands. Since allied charge attracts, positive side of bias voltage source attract the electron left end of P regions. Holes in P region acts as a medium or pathway for these electrons to move through the P regions. Electron move from one hole to the next towards the left. The holes move to right to the effective flow of current. Force is called hole currents. The depletion region become narrows. R limits the currents which can prevent damage to the diodes. Positive side of the bias pull the free electron in the N regions away from P-N junction. As losses of electron cause the additional positive charge are created, widening the depletion region. In P region, electron from negative side of bias entering the valence electrons and move from holes to holes toward the depletion region. As losses of holes cause additional negative ions are created. As a result, the depletion region wider than in forward bias. Voltage source of bias connections are negative to the P material and positive to the N materials. This condition prevents current through the diodes. Current flows is negligible. Small amounts of free minority electrons in P regions are pushed towards the P-N junction by the negative bias voltage. Forward bias voltage applies. There's current called forward current IF. Voltage applies less than barrier potentials in case current flows is very small, because of no enough voltage to overcome the barrier potentials. As forward bias voltage increase, current also increase. With applied voltage exceeding barrier potentials, forward current begin increase rapidly. But voltage across the diode increase only gradually is due to the voltage drop across internal dynamic resistance of the semiconductor. After 0.7 volts, voltage remain at 0.7 volts, but IF increase rapidly. As gradually increase reverse bias voltage, small reverse currents and voltage across the diode increase. When applied bias voltage reaches breakdown values, reverse current begin to increase rapidly. As increase the bias voltage, current increase very rapidly, but voltage across the diode increase very little above bias voltage.